This video will go over the graphs of basic functions. You may have heard these referred to in previous math courses as the parent functions. Another thing we're going to talk about besides the graphs is the concept of continuity. I'm going to give you an informal definition in this class because the actual formal definition involves the use of calculus. Basically, a function is continuous if when you're drawing the graph of the function, if you can draw the entire graph without lifting your pencil from your paper. Alright, so determine the intervals of continuity for each function in this figure. So, for this one we'll call it part A. When we're talking about the intervals, we're talking about for what values of x, for what intervals of x values is the function continuous. If you notice for part A, as it keeps going to the left or right, you can keep drawing it without picking up your pencil. So that would be the interval from negative infinity to positive infinity. Now you can never touch negative infinity, so you would use a parentheses. And you can never touch positive infinity either, so you would use a parentheses for that. Now for this one we'll call it part B. For the values of x where it's continuous, notice we have a discontinuity at 3, so it's continuous for all the x values less than 3, so from negative infinity to negative 3, to positive 3, But since it never touches positive 3, we would use a parentheses. And since we never touch negative infinity, we would use a parentheses as well. Now, it's also continuous for every value greater than 3, but not 3 itself. So it'd be from 3 to infinity, and again we'd use parentheses. Now let's talk about the graphs of some of the parent functions and where they're continuous and their domain and range and several other characteristics. Okay? We're going to start with the parent linear function, or your book refers to it as the identity function. The reason we call it the parent linear function the identity function is because if we plug in a particular value of x, we're going to get the same value out. For instance, if we plug in -2, we just get -2. If we plugged in -1, we'd get -1. If we plugged in 0, we'd get 0. Regardless of what number you plugged in for x, you always get the same number out. Here's what the graph would look like. Okay, here's the graph. Since there's no number being added on the end of our parent linear function, that's like adding 0, so you start at the origin. Since there's no number in front of x, we understand it to be 1, so our slope is 1. That means you go up 1 unit, right 1 unit, up 1 unit, right 1 unit. That's how we get the parent linear function. Now the domain, you notice it keeps going to the left or right. There are no discontinuities, so the domain is from negative infinity to positive infinity, and the range is also from negative infinity to positive infinity. And determine where it's continuous. It's continuous over the entire domain from negative infinity to positive infinity. And this also, to figure out where it's increasing, you notice as the x values increase, the y values are also increasing. So it's increasing from negative infinity to positive infinity as well. Plus, you also know in the negative direction, as the x values increase, the y values also decrease. And the next function we're going to go over is what your book refers to as the squaring function. It's just the parent quadratic function. Alright. And to figure out the particular values of y, for each time you plug in a value of x, if you were to plug in -2, that'd be negative 2 squared, which would be positive 4. If you were to plug in negative 1, you'd have to square negative 1, so that'd just be positive 1. Plug in 0, that'd be 0 squared, which would be 0. Plug in 1, you have 1 squared, which is 1. Plug in 2, you'd have 2 squared, which is 4. And the graph of the parent quadratic function would look like this, because you could plot your points 0, 0, which would be right here. Plot your points 1, 1, and negative 1, 1. Your points 2, 4. And your point negative 2, 4, and you could just connect them. Now, notice the domain, it keeps going to the left or right, no discontinuities, and it doesn't stop, so the domain would be from negative infinity to positive infinity. And the range, now the range, if you notice, it never goes below x or below y equals 0, but it does include the number 0, so it'd be 0 to infinity. And since it does include 0, we would put a bracket around 0 instead of a parentheses. Now, to figure out where it decreases and increases. If you notice, for the negative x values, as the x values are increasing on this side, the y values are decreasing. So it's decreasing from negative infinity to 0, but not including 0. And it's increasing from, now if you look at the positive x values, as x increases, y is also increasing, so it's increasing for the positive x values from 0 to infinity, but not including 0. And the quadratic function, it's continuous over the entire domain. As you go left or right in either direction, there are no discontinuities. So it's continuous on the interval negative infinity to infinity. Now the next type of function we'll go over is, your book refers to it as the cubing function. I've always referred to it as the cubic function. But it's just the parent cubic function. Cubic function, f of x equals x to the third. Let's start by creating our table of values. If you were to plug in negative 2, for the y value you'd have to cube it, so you'd have negative 8. Cube negative 1 to get the y value, so you'd have negative 1. Cube 0, you'd get 0. 1 for x equals positive 1, that'd be 1 to the third, which is 1, and for 2, that'd be 2 to the third, which would be 8. So if you were to plot your points, you'd come up with the following graph. Alright, we plot the point 2, 8, right here. Plot the point negative 1, 1, 0, 0, 1, 1, and then 2, 8. It'll be up here. So just draw a smooth curve through those points. Now if you notice, it keeps going to the left or right, so the domain would be from negative infinity to positive infinity, because there are no discontinuities. Likewise for the range, it keeps going in the vertical direction, so the range would be from negative infinity to positive infinity. Alright, as x is increasing, the y values are constantly increasing as well, so it's increasing over the entire domain from negative infinity to positive infinity. And it's continuous on the entire domain from negative infinity to infinity. The next thing we're going to talk about is what we call the square root function. Okay. Since f of x is equal to just the square root of x, and the way we get our table of values is if we plug in, say, 0, you get 0. Plug in 1, the square root of 1 is 1. Plug in 4, square root of 4 is 2. Plug in 9, the square root of 9 is 3. You notice we didn't include any negative numbers, because if you plug in a negative number into the square root, you get an imaginary number out. Like if you were to plug in, say, negative 4 rather, the square root of negative 4 would just be 2i. So that's why we don't include the negative numbers. That's why we didn't include the negative numbers in our table. So now if you were to plot these points to draw our graph, it would look like this, because you notice you plot the point 0, 0, the point 1, 1, point 4, 2, and if we had any room you could plot the point 9, 3 as well and just draw a curve connecting them. Now the domain, notice it's just all the non-negative x values, so it goes from 0 to infinity, but it can include 0 because the square root of 0 is not negative. And the range, it doesn't include any negative output values. So the range is just like 0, 1, 2, 3, etc., etc. So the range is also from 0 to infinity, but it includes 0. So that's why we do the brackets. Okay, it's increasing over the entire domain from 0 to infinity, because as the x values are increasing, the y values are also increasing. And it's also continuous on the entire domain. As you notice, there are no discontinuities on the entire domain, so it'd just be continuous from 0 to infinity. Alright, the next function we're going to talk about is something we call the cubed root function. Alright, so to do that, so to graph this, we can plot a table of values if you don't have a graphing calculator. Like say if you plugged in negative 8 for x, you'd get negative 2, because the cubed root of negative 8 is negative 2. The cubed root of negative 1 is negative 1. 0. Cubed root of 0 is 0. And the cubed root of positive 1 is just positive 1. And the cubed root of 8 is 2. The reason we chose these particular values in general, or the reason we chose these particular values, because earlier when we did the cubic function, we knew that negative 2 to the third is negative 8, so we should also know that the cubed root of negative 8 is negative 2. So now if we plot those points, we can come up with our graph. Alright, so you notice at negative 8, the y value is negative 2. At negative 1, the y value is negative 1. At 0, the value is 0. At x equals 1, the y value is 1. And at positive 8, the y value is 2. So if you just connect all those points, assuming you could actually draw better than me, which shouldn't be that hard, you would get that graph. So the domain, it keeps going to the left or right. So there are no discontinuities, so it'd be from negative infinity to positive infinity. And the range, notice it keeps going in the positive and negative y directions, albeit slowly, but it still keeps going, so the domain is still all real numbers, or all the numbers from negative infinity to positive infinity. And it's increasing Notice as the x values increase, the y values are still increasing. So it'd be from negative infinity to positive infinity. And it's continuous. There are no discontinuities, so it's continuous over the entire domain, from negative infinity to positive infinity. The absolute value function f of x equals, no, just absolute value of x, just an x in between two bars. The interesting thing about the absolute value function is that it's defined by different functions for different parts of the domain, which we'll get into now. Alright, the absolute value function when x is negative is defined by the negative identity function negative x, and when your x values are non-negative, meaning greater than or equal to 0, it's defined by the identity function f of x is equal to x. And here's a picture of the graph so you can know what I'm talking about. Alright, so notice for the absolute value function, for all the non-negative x values, it's defined by f of x is equal to x by the linear function, but it's defined by this function. You notice for this function you have to get from one point to the next, you have to go up 1, back 1, so it'd be up positive 1 in the y, back negative 1 in the x, up 1, left 1, up 1, left 1, so the slope would be negative 1 for this branch, and then positive 1 for this one. So the slope would be positive 1 for this side and negative 1 for the other side. That's why it's defined by two different branches. There's a table of values from negative 2, negative 1, 0, 1, and 2. You notice all the absolute value function just takes all the input values and makes them positive. So if you plugged in negative 2, you'd get positive 2. If you plugged in negative 1, you'd be doing this with it where you just change the sign, so you'd be positive 1. Plug in 0, you get 0. Plug in 1, you get 1. And plug in 2, you get 2. Now, the domain, since it keeps going to the left or right, it would just be, I don't know why I drew the squiggly brackets. It won't let me erase, so we'll just rewrite it. The domain, since it keeps going to the left or right, it'd just be all the numbers from negative infinity to positive infinity. And for the range, it never goes past this point right here. It never gets lower than that, but it does include 0 right here in this part. Since it includes 0, it'd be all the values from 0 to infinity, but it'd be a bracket around the 0. Now it's increasing from 0 to infinity. Now it's increasing for all the positive values from 0 to infinity, but not including 0. And it's decreasing for all the negative values from negative infinity to 0. Remember, the absolute value function is continuous over the entire domain, which in this case would be from negative infinity to infinity. So now we're going to practice graphing piecewise defined functions. For this one, now for x is less than or equal to 2. Now if you plug in 2 into this first part, this one, the negative 2 times 2 would be negative 4 plus 5 would be positive 1. So it'd start right there. Now since the slope is negative 2, it would go up 2, back 1. So that first branch would look something like this. Now for the second part here, if you plug in 2, it'd be 2 plus 1, which is 3. But since it has to be greater than 2, you cannot include 2 in this piece, so it needs to be an open circle. Open circle means it does not include that particular value of x. So now you can just go up 1, over 1, and graph that branch. Since it's a linear equation, all you need is 2 points. Your graph should look something like that. Now for part B, let's graph the first branch here, 2x plus 3, if x is less than or equal to 0. Plug in 0, you get 3 for the y-intercept. So, you go up 2, right 1. So up 2, right 1, which means, it means that since we're dealing with the negative x values, instead of going up 2, right 1, we would need to go down 2, back 1. Down 2, back 1, we could graph the line like that. Now, for the positive x values, if you plug in 0 into the second term, 0 squared is, negative 0 squared is still 0, plus 3 is still 3. So it'd still start here, so you can still do a closed dot, because it's already closed from the first branch. So if you plug in 1, you get negative 1 squared, which is 1, plus 3, which is 2. And then negative 2 squared. Negative 2 squared is 4. Actually, negative 4. Plus 3 would be negative 1. So you'd have kind of a curve right here, and your graph would look something like this. Now the last type of function we're going to learn about is what we call the greatest integer function. Alright, the greatest integer function, which is written with double brackets, it just pairs every real number with the greatest integer less than or equal to it. So like for instance, if you were to plug in negative 4, the y value would be negative 4. If you were to plug in negative 3.5, it'd still be negative 4, because that's the greatest integer. Negative 4 is the greatest integer that's less than negative 3.5. Like if you're plugging negative 1.5, the greatest integer would be negative 2. And here's what it would look like on a graph. If you notice, it's just a step function. For any decimal fraction, it's always equal to the greatest integer that is less than that number. So if, for instance, the greatest integer of 3.7 would just be 3, because 3.7 falls in this interval from 3 to 4. So the answer would be 3. Now the domain. If you notice, even where it's discontinuous, for all the open circles where it's discontinuous, if you go up, it's still defined for that value of x. So it's from negative infinity to positive infinity. And the range, we don't have any decimal numbers or fractions in the range, it's just the set of integers. So it would just be the set of all y values such that y is an integer. Alright, I'm going to use the shorthand notation for integer. This symbol here that looks kind of like an E, that's the symbol that means contained in. So y is contained in. And the script letter Z, that's the symbol for the set of all integers. So what the set of all y values such that y is contained in the set of all integers. Now, notice y, it's actually constant on all these little intervals. So you can't really say it's increasing because it's not constantly increasing. And it's discontinuous at the all integer values. Like -3, -2, ... -1, ... We know it's discontinuous at all the integer values because you have the open circles. Alright, so here's an example of using the greatest integer function. It says an express mail company charges $25 for a package weighing up to 2 pounds. For each additional pound or fraction of a pound, there's an additional charge of $3. Graph the function for the interval from 0 to 6 pounds. So let's go ahead and draw a graph. And after I illustrate the concept, I'm going to put up a nice clean picture, nice neat picture for you. Alright, so you have to pay $25 because let the y-axis be the axis showing the money. It costs $25 from 0 to 2 pounds. It says for each additional pound there's an additional charge of $3. So if you go up to 28, that'd be from 2 to 3. If you add another $3 for a package weighing from 3 to 4, that'd be $31 for a package weighing 3 to 4 pounds. It has to weigh at least 3 pounds. Or not at least, it has to weigh more than 3 pounds, but no more than 4, so weighs 31 pounds from 3 to 4. And the reason we did it like this, the open circles on the left end, is because it costs $25 because it has to weigh up to 2 pounds. But it cannot weigh 0 pounds because then you wouldn't have a package at all. It has to weigh up to 2 pounds. Alright, and that interval for 28, that's for a package weighing more than 2 pounds, so it'd be from 2, and it can weigh up to 3 pounds for it to cost $28. And if it weighs more than 3 pounds and up to 4 pounds, it'd cost you $31. And that should be a bracket around the 4, because it can weigh up to 4 pounds for it, and it still costs you $31. So I think you should get the idea at this point. So let me put up what the graph should look like. Let me put up a nice neat picture of what the graph should look like. Here's a neat picture of what the graph would look like up to 6 pounds. So if a package weighs at least 5 pounds and up to 6, then it looks like it would cost $37.